Yeah, it's a pleasure to be here. I already had very nice discussions, and I'm looking forward to more very nice discussions. And so today I will talk about quantum classical hybrid theories, which are theories that involve both classical and quantum degrees of freedom. And I will talk about two examples in particular. One is feedback control, where the classical degree of freedom is the outcome of a measurement that is then being fed back to a quantum system such that we have a dynamical interplay between this classical measurement outcome and the quantum system. And the other example is where we have a small quantum system that couples to some environment, and the environment can be described with a classical degree of freedom. And so we also have a dynamical interplay between the classical degree of freedom and the quantum system. And here the idea would be to use the small quantum system in order to manipulate the environment and in particular to cool it down or to purify the environment. So let me start by motivating why we should care about quantum classical hybrid theories. And well, as we all know, the macroscopic world around us that we see every day behaves approximately classically. So that's where we get our everyday intuition. But then when we go to small systems or cold systems, we have interesting behaviors such as quantum superposition and entanglement. And this is nicely illustrated by this sketch of Zurich, where we have the quantum regime here and the classical regime on the other side, and there's some kind of border territory. And the goal is, of course, to kind of control these kind of quantum system and to make use of this interesting behavior. On the one hand, we would like to better understand how the world functions as physicists. And on the other hand, we also want to exploit these kind of interesting features for technological applications. But in order to control these quantum systems, we do somehow need to make a connection to this classical world, because when we make a measurement, we need to have something that we can read off of a screen in the end. We need to have a measurement outcome that behaves in a classical way. Similarly, the environment of a quantum system sometimes can also be described using classical degrees of freedom, and this kind of motivates the need for such quantum classical hybrid theories. And I think it's really best illustrated in feedback, where we have this dynamical interplay where the measurement outcome has information on the quantum system, but then the dynamics of the quantum system is again influenced by the measurement outcome. And more recently, these hybrid theories have also been put forward as a method to describe the effect of gravity on quantum systems. So this is there was this PRX by Jonathan Oppenheim, who discussed this in some detail, and it's an attempt to kind of circumvent the quantization of gravity, because that seems to be really, really hard. So maybe we can get some effective theories by treating the gravitational field as a stochastic classical degree of freedom that then interacts with the quantum systems that we are interested in. Right. So the rest of the talk is now split into two parts. I will first talk about feedback control, and then I will talk about finite size environments that we want to purify, where the classical degree of freedom is in the environment. Right. And feedback control is really an enabling technology that makes things possible, such as cooling down, levitating nanoparticles close to the ground state, like in the experiment here on the left-hand side. Also in quantum error correction, it's an important ingredient here for superconducting qubits, and it also enables curiosity-driven research projects, such as the one to the right, where they caught and reversed a quantum jump in mid-flight. And one of my contributions to this field was the development and derivation of the equation that I show you here, which we call the quantum Fokker-Planck master equation. And so this equation describes systems that are continuously measured and undergo feedback, and in certain cases it enables analytical description or analytical solution for problems where before there weren't really any techniques to get to these analytical results, right? And so the sketch that I show you here again it illustrates some of the parameters that we use. So we think of a detector that always couples to a quantum system, and this detector has an outcome D. So at all times do we get such a measurement outcome D, and we then feed this measurement outcome back to the quantum system, right? Now, the quantum Fokker-Planck master equation may look a little bit intimidating when you first see it, but I would like to now take you through the terms kind of one by one, because we can interpret them, all of them, in a fairly illustrative way. And so I would like to start with the left-hand side, where we have this central object of the equation, this rho t of d, which is an operator that is also a function of the measurement outcome d. And it really provides a joint description of the quantum system and the measurement outcome. So if we integrate out the measurement outcome, if we integrate out this d, then we get a density matrix that describes our quantum system.
By d you mean measurement outcome at a given moment, or
yes.
whole history?
No, exactly. So the rho t of d describes the system and the measurement outcome at the time t, not the whole history yet. That is important. Similarly, when we take the trace over this object, then we get a probability distribution for the measurement outcome. Right. Now, the first term on the right-hand side describes the feedback controlled dynamics of the system. So this calligraphic L could be a commutator with a Hamiltonian for a closed quantum system, or it could be a Lindblad master equation. Importantly, it depends on the measurement outcome, because we think that maybe we change some parameters in the Hamiltonian based on the measurement outcome that we get by applying some electric or magnetic fields, for instance. Right. All the other terms, they involve the detector. And they have two important parameters that we need for this theory. One is this lambda, which denotes the measurement strength, and it tells us how much information we get from our continuous measurement. Now, if we get information in a measurement, there's always also some back action, so we have some sort of collapse of the wave function, and this is described by this second term on the right-hand side, this term here. The other parameter of the detector is the bandwidth, gamma, and this tells us how fast our detector will react to changes in the system. Right. Now, in this back action term, in this dephasing term, we introduced also this operator A, and this is the operator that we want to measure. So if we want to make a measurement of a position of a particle, it will be the position operator. And then this term describes dephasing in this eigenbasis, so it tells us that we tend towards the measurement drives us towards the eigenstates of the measured operator, which is what we expect. Right. The last two terms on the right-hand side, they describe the dynamics of the measurement outcome, and they include a first derivative as well as a second derivative. And so this is kind of the Fokker-Planck part of this equation, because in a Fokker-Planck equation you get these kind of terms, and they would be called drift term for the first derivative and diffusion term for the second derivative. Now, the drift term ensures that the measurement outcome goes towards the eigenvalues of the measured operator. So if our system is in an eigenstate of the operator we want to measure, the measurement outcome D will drift towards the corresponding eigenvalue, and this is how we can argue that indeed we make a measurement of this operator A. The last term, the diffusion term with the second derivative, tells us how much noise we will have in our measurement outcome. And you can see the larger the bandwidth, the larger the noise. And this is to be expected because fast detectors usually also have more noise. And it's also inversely proportional to the measurement strength. So the stronger we measure, the less noise we're going to have in our outcome, which also makes a lot of sense. Right.
So how much is put by hand in this equation, and how much is derived, like, fundamentally?
Well, that depends what your standards for a fundamental derivation is, I guess. So this is derived from time evolution with this calligraphic L interspersed by Gaussian Krauss operators. So we don't have a microscopic model for the detector, but it does describe continuous measurement as it's usually described using Gaussian Krauss operators. And then you can derive this from that. Right. So this, yeah, yes?
Some restriction on the bandwidth, no? This works for any bandwidth?
In principle, yes. What I do think one has to be careful is, of course, it depends what this calligraphic L is, right? If you put in a Lindblad master equation, in this Lindblad master equation there are some assumptions on timescales that you might start to violate when you go too crazy with your bandwidth. If in this if in this calligraphic L you simply put a commutator with a total Hamiltonian that describes everything, I don't think there's any, as long as your Gaussian-Krauss operator description is okay for a continuous measurement, this is okay essentially.
Gaussian-Krauss operators you mean in terms of position momentum, right? Or what?
No, so the Gaussian-Krauss operator really involves then this measured operator A. So you have, you discretize your time, and at each time step you have Krauss operators that are Gaussian, and in the exponent you have this operator A. So at each point in time you get a noisy outcome of a very weak and noisy measurement of A, and you combine those into a continuous measurement. And then you take the continuum limit. Right, and so this equation can be applied to different continuous measurement scenarios, such as charge sensing, or in quantum optics, homodyne or heterodyne detection. And I briefly would like to explain how charge sensing works, because I will also use it then in an example where we do a theory work, right? And so this is an example taken from the lab of Willem Meisy at Lund University. And what you see here horizontally is a nanowire, and the colored areas are quantum dots. And we are interested here in this blue quantum dots, and this quantum dot is connected to this electric contact. So a single electron can jump onto this quantum dot and off this quantum dot. So you can have 1 electron or 0 electrons in this quantum dot, and the idea is now to measure the occupation, to measure the charge of this quantum dot, so to measure if there is 1 or 0 quantum dots. And this is being done by this right part of the system, this purple quantum dot, which is connected to 2 contacts, and there's a current going through this purple quantum dot. And this current will depend on the number of electrons in the blue dot, because, well, electrons repulse each other, so if there is an electron, it will be felt by this purple dot, and it will change the current. And indeed, in the bottom you can see a time trace of a measurement of this current through the purple quantum dot, and it jumps between 2 values. One value corresponds to having 0 electrons on the dot, on the blue dot, and the other value corresponds to having an extra electron on the quantum dot. So what we can see in this trajectory is we can see in real time how electrons jump on and off this blue quantum dot. And to connect now with our quantum Fokker-Planck master equation, in our case, the measurement outcome now would be this current, this blue line. Right. On the theory side, the quantum Fokker-Planck master equation has been applied to a few problems. For instance, the cooling and trapping of a particle in a harmonic potential, a Maxwell-Demon scenario that I will talk about in more detail, and also an entanglement generation protocol where feedback is used to enhance the entanglement between 2 qubits. So now I want to talk about this Maxwell-Demon, and what you can see in this sketch on the right is 2 quantum dots that are connected each to an electronic reservoir. And there is a voltage bias between the 2 reservoirs, which is illustrated by this kind of battery. Now, the second law of thermodynamics would tell you that the current will go with the voltage. The voltage will move electrons through this double quantum dot, and the battery will discharge. Right. Now the idea of Maxwell's demon is to use microscopic information and feedback in order to do things that seem to be not allowed by the second law of thermodynamics. So here we want to make charge measurements of the quantum dots. We want to measure if there are electrons or not with these 2 detectors illustrated here. And then based on this measurement outcome, we're going to move the energy levels of these quantum dots in a way that the electrons are forced against the voltage bias, so that we actually are charging the battery, which seemingly violates the second law of thermodynamics. And now here we have 2 detectors, and on the left is illustrated how the measurement outcome that is now 2-dimensional, how it contains the information on the state of the system. So the system can be in 3 different states. It can be in the state 0, which is here, where there's no electron on the double dot. And then the measurement outcome would diffuse around this point. Then when an electron jumps into the left dot, the measurement outcome drifts down here and diffuses around this point. When the electron jumps into the right dot, the measurement outcome drifts over here and diffuses around that point. And these are the only three states that we allow. We say that the electrons repulse each other so much that there can only be one electron or 0 electrons in the system, right? And now I want to explain to you how we can use now the information on where the electron is in order to move it against the voltage bias. So what you can see here is our energy diagrams. And the lines here denote the energies of the quantum dots, and these boxes denote the contacts. They are at a different chemical potential, which is this mu L and mu R, and the potential difference is exactly the voltage bias. And now assume that we are in this empty state. There's no electron in the system, and then we're going to put the energy levels like this. And so the only thing that can happen here is that an electron jumps in from the left. The level on the right is too high in energy. No electron can jump in there. As soon as we see that an electron entered, we're going to move the levels down according to the dashed arrows, and we end up in this configuration. And now we have trapped the electron, because now there's no empty states that the electron could escape to. So the only thing that can happen is that the electron tunnels between the left and the right dot. And as soon as we see that it moved to the right, we're going to move the energy levels up according to the dashed arrows again. And then we're in this scenario where the only thing that can happen is that the electron will leave to the right. And that brings us back to the initial kind of configuration. Now in such a cycle, you can see that we moved one electron from left to right, so from a lower to a higher chemical potential. And this provides electronic work or chemical work, which is equal to the voltage bias, which is simply the difference in chemical potential. Now this energy has to come from somewhere, and in this case it comes from heat. So we're actually cooling down the electronic reservoirs in this process by the same amount as the work that we obtain. So the system really does what a kind of a Maxwell-Demon scenario is supposed to do. It turns heat into work using information, and according to the second law this should be prohibited, but the fact that we have information on the microscopic states allows us to do that, right? And now a few years back we looked at the classical version of this device, and now with the quantum Fokker-Planck master equation at hand, we can actually look into the quantum mechanical version, and we can ask, well, what is the role of quantum coherence in this system? And quantum coherence here means that the electron can be in a superposition of being on the left dot and on the right dot, which is what is illustrated in these kind of cloud, in these green clouds in configuration 2 and 3. And right away we can assume that, or we know that there is going to be a trade-off, right? Because if we make a very strong measurement, we will run into the quantum Zeno effect. So if you measure a system continuously very strongly, you dephase it, and that prevents any coherent tunneling. So that would prevent any transport. The system would just be stuck in a state. So that cannot be good in extracting work, right? And we can't move the electrons from left to right. But if we make a very weak measurement, on the other hand, we don't get any information, and then we can also not do much. So the measurement cannot be too weak or too strong. That one can already say from the outset. And this is indeed also what we find. And now I mentioned that the quantum Fokker-Planck master equation allows for obtaining analytical results for certain scenarios where before this wasn't possible. And this is one of them. It's a very nonlinear feedback protocol. And in the limit where the detector is much faster than the system, where the detector has a large bandwidth, we can get analytical results. So here I show you the analytical result for the power. And we can learn quite a bit about the system from this result by looking at the numerator. So there are a bunch of terms in the numerator. The first one is the difference in chemical potential. That is natural that it appears because that's the energy scale that we're working with here. Then the second bracket is 1 minus eta, where eta is an error probability. And that tells us that the more errors we make, well, the less power we will get out, right? So that error probability depends on the measurement strength and on the bandwidth of the detector. And then we have 3 different tunnel rates, and these describe the transport through the system. So gamma L describes the transport into the left dot, kappa R describes how the electron leaves to the right reservoir, and the psi is an effective tunnel rate between the left and the right dot. So it's given in this equation explicitly. And it depends on the tunnel rate G, the tunnel coupling, but also a bunch of other terms. And I highlighted here in blue the measurement strength because that encodes the Zeno effect. So we see if we make a very strong measurement, lambda becomes very big, and then the psi will decrease with lambda, and that will block any kind of transport, and that is exactly the Zeno effect. We also have the term in red, which at first puzzled us quite a bit, because we thought, well, the tunneling here happens in configuration 2, where the two energy levels have the same energy. So why would the energy splitting in this other configuration 3 matter for this tunneling? So at the beginning we didn't understand this, but by now we understand that this is a Zeno-like effect that comes from feeding back noise. Because when we make measurement errors here, what can happen is that we randomly shuffle between the configuration 2 and 3, even though the electron might not actually move. Right? So we have the energy levels and we randomly move it up and down like this. Now if you randomly move around the energy levels of a quantum system, you introduce dephasing, right? And here we are in a fast detector limit, so we would do this very fast actually. So this would result in considerable dephasing, and this is very similar to the dephasing you have in a measurement. So it will also kill off-diagonal elements, it will also block any kind of transport, and it will give you an effect that is very much like the Zeno effect, but it is due to the noise that we're feeding back to the system because we make measurement errors, right? And this kind of system here, we nicely see it analytically for a nonlinear feedback protocol, but of course this also happens for other feedback systems. It's not something that is unique to the system that we're looking at, right?
So you say you want to put it to 0 or no? Difference in epsilon u, epsilon 0.
No, if you put it to 0, then the electron can go back to the left, right?
Ah.
So we can't avoid it. We have a bunch of trade-offs in this system because we want a bunch of things, right? So
how are the epsilons dependent on the errors? Because it depends on the measurement, but is it the error of the measurement of what's the energy of the level, or the error of how we set it?
Right, so maybe for this I can go back, I can come back here. So here on the left you see the measurement outcomes, right? Now we say whenever the measurement outcome is in this quadrant, we assume that the system is in the state L, and we're going to put the energy levels here. Whenever the measurement outcome is here on the right, we're going to put the energy levels like this. Now, if your measurement outcome is noisy, it will cross this line a bunch of times. And that means we're going to randomly shuffle back and forth, even though the system might not even evolve during that time. And it's that random shuffling back and forth that introduces noise and dephasing to the system.
Thank you.
Right. Now, the quantum Fokker-Planck master equation also allows us to investigate the system across the quantum to classical transition. And I illustrate this here with trajectories. So this on the horizontal axis here you have time, and I show you here density matrix element for a given realization of measurement outcome. So you can think of this as what happens in a given experiment. And in the upper panels we have the diagonal density matrix elements, and in the lower panels we have off-diagonal density matrix elements. And on the left I show you a relatively weak measurement, and on the right I show you a relatively strong measurement. Now you see for the weak measurement, in both cases I show you a transition from the left state. So here the system is in the left state to the right state, and the same over here. We go from the left to the right. And on the left for the weak measurement you see that this transition is kind of, it's a bit messy. We have some oscillatory features and some stuff is going on. And to describe this we really need the full quantum model. We need the quantum Fokker-Planck master equation. When we have a stronger measurement, we can actually treat the quantum tunneling perturbatively, because now these transitions happen really fast and there is only coherence around this time where they happen. So we can treat the quantum tunneling perturbatively and actually derive a classical rate equation for our system. And we were very happy with this because we actually re-derived the classical model that we heuristically used when we investigated the classical version of this device. So now we can actually derive this from a quantum model. And that means we now have a quantum model and a classical model, and we can compare them and ask things like, is a quantum model, does it predict more power or less? Is quantum coherence beneficial or detrimental for extracting power? And the answer is it depends, right? So this is what I show you here. I show you the power. The solid lines are the quantum model, the dashed lines the classical model. Extracted power is negative here, so we want power to be as negative as possible. And on the left, I show you a relatively slow detector, relatively small bandwidth, and on the right, a faster detector. And for the slow detector, we find that the quantum model actually predicts more power, so quantum coherence seems to be beneficial to extract power. On the right, it's the other way around. Quantum coherence seems to be detrimental. And we can understand this again in terms of this second kind of Zeno-like effect, because for a fast detector, this manual dephasing will be more pronounced, and it punishes the quantum model, but the classical model doesn't care about that. Whereas for a slow detector, this manual dephasing seems to be less pronounced. So there we don't have analytical results, but this seems to imply that there this Zeno-like effect is less pronounced, and so the quantum coherent model actually outperforms the classical rate equation. Right, so this brings me to the conclusions of this first part. So I talked about this quantum Fokker-Planck master equation, which can provide analytical insight into nonlinear feedback protocols. And I showed you this example of this Maxwell demon, where we see this analytical insight in particular with these kind of two Zeno effects, and also with what happens across the quantum to classical transition. Right, and this brings me to the second part of the talk, where I will talk about finite size environments that are being cooled down using a quantum system. And this is heavily motivated by experiments. So there have been a bunch of recent experiments where a small quantum system, in particular a qubit, was used to manipulate and purify or cool down its environment. On the left, you see an experiment on a superconducting qubit that was used to cool down the environment of two-level systems in a so-called Szilard engine protocol, which is another type of Maxwell's demon. And in the middle and on the right are experiments on a semiconducting qubit, semiconducting spin qubit, that is used to manipulate the environment of nuclear spins and purify the nuclear spins, and this results in enhanced coherence time. And these kind of experiments really demand for new theoretical methods, where we would like to somehow get some effective theories that describe this, but that don't need us to describe all the degrees of freedom of the bath, because that's often hopeless, right? And one avenue for this, a promising avenue, is provided by the so-called extended microcanonical master equation, which is an approach that goes back to Heinz-Peter Breuer and colleagues, and has more recently also been used by Philipp Strassberg and co-authors. And I briefly want to explain what the spirit is of this approach. And so when we have a system like is sketched here, where we have a system and an environment, and we want to describe this theoretically, the thing we would often start with is a full unitary description of everything together. So we have a total density matrix that obeys this von Neumann equation with a total Hamiltonian. And solving this equation is often hopeless, because the environment is assumed to have many, many degrees of freedom. So it's nice to have approximations that give us simpler equations. And the most prominent one are probably the Bohr-Markov approximations, where we make a set of assumptions that allow us to, so this on the left here. So we make a set of assumptions that allow us to derive a Lindblad master equation for the system alone. But now this is not good enough, because now we want to see how the environment actually changes. But in the Lindblad equation, you traced out the environment. You don't have any information on it anymore. Right. The EMME does allow to keep track of some parts of the environment. In particular, so you make a set of assumptions that are quite similar to Bohr-Markov, but you keep track of the energy of the environment. And in the end, you get an equation of motion for this rho of E, which is very similar to the rho of D we had before, but E now denotes the energy of the environment. So we can keep track of the probability distribution for the environment, and also correlations between the energy of the environment and the quantum system. Right. And now we adapted this to the scenarios that I showed you in the experiments before. In particular, for a semiconducting quantum dot, where we have this type of total Hamiltonian motivated by this experiment in the group of Richard Warburton at the University of Basel. And then we also looked at a superconducting qubit scenario coupled to a bunch of two-level systems motivated by this other experiment that I showed you before.
So can we think of this model as kind of like classical stochastic process that drives this quantum master equation? That this energy changes is like a classical stochastic process?
Yes, but like in feedback, you have a dynamical interplay, right? The quantum system can manipulate the environment, and the environment again affects the quantum system.
So it's not given in stochastic.
It's not a fixed stochastic process, exactly. But yes, then absolutely. Right, and so adapting the EMME to these scenarios was actually quite non-trivial, but a PhD student in my group, Marcelo Janovic, was able to derive the equation that I show you here in the bottom. And now I slightly changed the notation, so here we have rho m instead of rho of E, and m denotes the magnetization of the environment. So it tells us how many spins point up and how many point down. And then you see there's a Hamiltonian part where the Hamiltonian depends on the magnetization. And this is nothing else than the fact that the magnetic field that is felt by the qubit depends on the magnetization of the bath. And then we have a bunch of jump terms that look kind of similar to the jump terms you get in the Lindblad master equation, but now they don't only change the quantum system, but they also change M. They also change the magnetization of the environment. So this is where this dynamical interplay comes from. And now in both of these experiments, the idea is essentially that we initialize our quantum system, we let it interact with the bath, and then we reinitialize, and then we do that a bunch of times, n-r times, and this allows us to kind of cool down the environment, to purify it. And so I now want to illustrate how this works with this qubit Szilard engine a bit in more detail. So we start out with this Hamiltonian. We have a qubit with a splitting omega s, and a bunch of two-level systems that are resonant with the qubit. So this I is a collective spin operator, and then we have this kind of coupling. And from this Hamiltonian, you can get the EMME that is shown in the bottom. And so indeed, the Hamiltonian is simply the Hamiltonian of the qubit plus essentially a Zeeman term that depends on the magnetic field of the reservoir. And then the jump terms, they are simply raising and lowering operators in the eigenbasis of the Hamiltonian. And what we can see here is, for instance, by relaxing the qubit, we can excite one of the two-level systems in the bath and vice versa. Right? So this is illustrated here. We have this kind of flip-flop processes.
So in fact, it's a collection of equations, yes, for all m.
Yes. You can either see it as a collection of equations, or you can see as m exactly. Very similar to the row of D we had before. But then D was continuous, now m is discrete. Right, now in the experiment, what they do is they cool down the environment. And they do this in this kind of protocol. So they initialize the qubit in the ground state. Then they let the system interact with the environment. And then what can happen is the two-level system relaxes, exciting the system. And that after some time, they measure the system and reinitialize it in the ground state. Right? And then you're back at the initial configuration, but you have cooled down or de-excited one of the two-level systems.
So
yes?
Are you post-selecting only on the events when the qubit relaxed?
No. No. So you don't post-select, but sometimes you will have an event like this happening. Sometimes nothing happens. If this happens twice, it's like nothing happens, right? So you go like this. So sometimes you will have de-excited the two-level system, sometimes the two-level systems remain the same. So there's no need to post-select. Right, and so by doing this, we can kind of cool down the environment one two-level system at a time. And with the EMME, we can now do some calculations, and this is what we find. So in a single one of these cooling strokes, we initialize the system in the ground state, and it goes to a maximally mixed state. We start here, the environment in a high temperature state, so its magnetization is 0, and it goes to -1/2. And this is exactly because what you mentioned, that there is a probability of 1/2 that we actually de-excited the two-level system, so the magnetization goes down by 1/2. And on the right, I show you the probability distribution of the magnetization as a function of the different cycle times. And you see, the more we repeat this, the more we're cooling down the environment. This peak kind of it narrows and it moves to the left. And it really becomes important once we have as many cooling strokes as we have qubits in the environment. And here we have like 1,000 two-level systems. Right. This is kind of the most naive approach, I would say, to purifying the environment. What we can also do is we can use correlations between the system and the bath to do interesting stuff. And I briefly want to talk about how this can be done here. So here we consider correlated state that looks like this. So this is a state where we have a given probability distribution of the magnetization of the environment. And then we have a quantum state that depends on this, on the magnetization. So for the moment, we're not asking really where these correlations come from. We're just asking if we have correlations, what can we do with them? And now we can envision a state like this, where for positive magnetization, we initialize the system in the ground state, and for negative, we initialize in the excited state, right? And so that means that for positive magnetization, we are cooling, but for negative magnetization, we are heating up because we start the system in the excited state. And if we initialize this state 1,000 times, then we're able to go from this red distribution to this blue distribution. So we can create a strong narrowing of the distribution around 0. Right. Now this state is rather artificial. We just wrote it down because we thought this is probably the best you can do when you want to narrow this distribution. But we can also look at states like this that you could in principle create by letting the system evolve freely under the magnetic field of the environment. And now note that this is the X basis. So this state winds around the Bloch sphere. So sometimes it's in the excited state, sometimes in the ground state. Whenever it's in the excited state, we get heating. Whenever it's in the ground state, we get cooling. Yes?
Why in the first case it wouldn't work with a mixed state? Why do you need a superposition? Just for what if I prepare the mid, like I would toss a coin rather than create a superposition? Why would that not work? Just to understand why you need coherence.
So this is actually, you don't have coherence, right? Because if M is positive, you just have the ground state. And if M is negative, you just have the excited state. So these prefactors, they are never both, there's no M where they both appear. It's either either you have the ground state or the excited state.
So why do you write it as a pure state? It's actually a...
Because for a given M, it is a pure state, right? For a given M, you have the ground or the excited state. But then when you integrate over M, you would have a mixed state. Actually, completely mixed state in this case. Right. Now in the state below, we're winding around the Bloch sphere. So sometimes we would have heating, sometimes cooling.
How do you know the magnetic field is in X direction?
So again, here we are just writing this down because we cannot, like actually in this superconducting qubit scenario, there is no way to turn off the energy exchange between system and environment because they're resonant. So we can't let the system evolve freely under the magnetic field of the environment. But if we assume we can do that, then we could also assume that we can do rotations, right? So we do some rotation, well, we initialize in a superposition of up and down, we let it evolve, and then we do a pulse. And then we get this state, so to speak. Right. But this state, if you think of in the Z basis, sometimes it will point up, sometimes down, depending on M. And now if we choose different taus, this is maybe a bit small, but if we choose different taus, we can get different effects. So for a relatively small tau, we still get a narrowing. This is this light blue distribution that's maybe a bit hidden. But if this tau is bigger, this winding becomes relatively fast in M, and we have heating, cooling. And this now gives us such a comp structure. Because for each of these peaks, on the right of it, we are cooling, and on the left of it, we're heating. So we can create kind of interesting states, and potentially we want to avoid some resonances in the environment, so maybe it's good enough to have a bunch of peaks, right? Right, but this model, it really serves to kind of understand what we can do with these correlations. So now, in the last few minutes, I would like to talk about the semiconducting qubit scenario, where we're also collaborating with the experimental group in-house of Richard Warburton. And here we have a Hamiltonian that at first sight looks a lot more complicated. So for instance, now we have a big splitting in energy between the system and the nuclear spins. So the nuclear spins have a much smaller splitting than the qubit of the system. And to compensate for this, we add an external drive, which is a Rabi drive, which here in the Hamiltonian appears as this omega times sigma x. And this delta is then a detuning, right? And the interaction between system and environment looks maybe rather complicated. But once you derive the EMME, we get something that looks very similar to the superconducting qubit scenario from before. We again have a Hamiltonian that is essentially the free Hamiltonian plus the magnetic field of the bath plus some lamp shift terms that I will ignore here. And then the lowering operator, or the jump operators, are again lowering operators, but now the quantization axis depends on m, right? You can also see this because of this Rabi drive, also the quantization axis of this h, of this Hamiltonian, right? The eigenbasis of this Hamiltonian depends on m, and this is also reflected in this lowering operator. But we still essentially have that the terms, they increase or decrease m by lowering or exciting the qubit, just now the basis depends on m, right? Now, another important difference is that because we have this big splitting, we can actually use that. Because if we turn off the Rabi frequency, then we can prevent any energy exchange between system and bath because they're simply not resonant. And so these rates that appear in the EMME, they go to zero as we turn off the Rabi frequency. And that means that we can actually create this kind of time evolution. So we can really let the system evolve freely under the magnetic field of the bath. And this allows us to create these kind of states that look very similar to the kind of states that I've shown you before, right? And indeed, we now can simulate the EMME and we get very similar behavior from before. We again can get these very peaked structures. So now again, the red is the initial distribution of magnetization. And after initializing 1,000 times, we can get this very funky distribution of magnetization in the bath and create these very special kind of states. And now the splitting between these peaks depends on the time that we let the system evolve freely with the bath, right? What we can now do is we can sweep this time. We don't choose a fixed time, but we sweep it. And then we can actually get rid of all the satellite peaks and create a very purified environment. And this is essentially what they did in these two experiments. And now this is really preliminary results. So we're now, together with the group of Richard Warburton, working on getting quantitative agreement between experiment and theory. But they do see, at least qualitatively, these two kind of behaviors when they perform these kind of experiments. So that looks very promising, that the EMME actually provides a useful tool to describe these kind of experiments. Right, and this brings me to my conclusions. So I hope I could convince you that these classical quantum hybrid theories can be very powerful tools to describe open quantum systems. I talked about feedback and how the quantum Fokker-Planck master equation can give analytical insight into nonlinear feedback protocols. And I also talked about finite size environments where the EMME provides an efficient treatment of large but still non-Markovian environments. Right, and with this I come to an outlook. So in terms of feedback, we are currently working on better understanding the thermodynamics of this quantum Fokker-Planck master equation. Since it's still a rather new equation, we don't fully understand how we should quantify information, quantify entropy production, get things like fluctuation theorems out. But then once we understand this, we also want to apply this equation to interesting phenomena. For instance, there are phase transitions that can be induced by feedback, and we hope that we can get some analytical insight into this exciting phenomena. And also, we would like to use feedback to design dissipative processes. Because what we can do is, for nonlinear feedback protocols, we can derive Lindblad master equations for the reduced system, integrating out the measurement outcome if the detector is fast. And so that would allow us to really design kind of Lindblad dissipators using feedback, and then in the spirit like environment engineering, we could potentially create non-reciprocal devices like non-reciprocal amplifiers and things like that using feedback and really getting simple theoretical descriptions of these. In terms of finite size environments, we're now working hard on getting quantitative agreement with experiment. And then we want to leverage this insight that we have now to get to better and faster purification protocols. We also want to make use of these very non-Gaussian features that we can create in the bath. So it's a bit unclear at the moment what they are going to be useful for, so we want to better understand them and actually put them to use to do some interesting stuff with them. And finally, we started just recently a project on describing gravity, where we can follow the seminal work by Coffey, Taylor, and Milburn, who asked, what if gravity can be effectively described using a feedback channel? But they were limited to linear feedback, and their result, the model that they came up with could be ruled out by experiments because it had too much noise. Now, with our nonlinear feedback and having access to this bandwidth, we hope that we can kind of get rid of this noise and have some kind of model that could effectively describe the effect of gravity that would be, that at least can't be ruled out by experiments so easily. Right, and so with this, I would like to thank the team, in particular Marcelo Janovic on the left, who worked on the EMME, and Kasper Prech, who is working on the quantum Fokker-Planck master equation. And I would like to thank all of you for your attention.
Thank you very much, Patrick. Thank you also for keeping on time. So we have time for questions. On the floor. Yes, please.
So you talked about this dynamical entropy sometimes. What is it exactly in the dynamical entropy?
Dynamical entropy? In the outlook. Right, so not really dynamical entropy, entropy production. Right, so the second law of thermodynamics, you can usually write it as entropy production is positive on average. And if you want to go more refined, you can argue that entropy production becomes a fluctuating quantity for stochastic processes, and then you have a fluctuation theorem. And if you have feedback measurement in information, then entropy production actually can become negative on average, but it's bounded by the information that you obtain. And we don't know how to quantify all of these objects actually for the quantum Fokker-Planck master equation yet. We're working on it, we have preliminary results, and it seems to work out, but especially in the quantum scenario, it gets a bit tricky.
Thanks for the talk, by the way. I wanted to ask, so in the Fokker-Planck equation, to derive it, you have your Gaussian outcomes, no? Like
Yes.
And then you filter them with a low-pass filter?
Yes, exactly.
And how crucial is your assumption of a filter, like to get your equations? Can you get also Fokker-Planck equations having different types of filters?
That is a very good question. So the filter is crucial because without the filter you have white noise. And that's what prevented Weismann and Milburn to do kind of nonlinear feedback protocols, because you can't take arbitrary functions of white noise. It doesn't work. Right? And so with the filter, we can afterwards take arbitrary functions of this. Now, the low-pass filter that we use preserves the Markovian structure. Right? So we do get a quantum Fokker-Planck master equation that only depends on the current value of d and not any previous one. There's other functions where this also should work. And so one collaborator, Guilherme de Souza, who works with Christopher Czarczynski, he is currently looking into, and he's been for a while, for instance, what happens if you put multiple filters in a row? Then you can still do something like that. But more importantly, what we're now trying to do is to replace the low-pass filter with the band-pass filter. And then you can still get something like this, it seems. But the price you pay is you kind of have two different measurement outcomes, because now your measurement outcome is an oscillating thing. So it kind of behaves like, not like an overdamped Langevin equation, but like an underdamped Langevin equation, where you would need x and p coupling to each other. And so we think we can get something similar. If you try to think of arbitrary filters, I think very quickly you run into the problem that actually you need the whole history of D to do something.
Any more questions? Please. Okay, just one more.
Something like 20 years ago, we were trying to simulate very simple enzymatic reactions, which actually corresponds to the system which you call finite size environment.
Mhm.
And I just started thinking if I could take your model and try to simulate such a process, I would have problems.
Okay.
Mainly, the first problem is the following. Suppose, okay, let's think about something which is well defined. So we have something like 1,000 atoms, and say 15 of them are in a quantum domain, right? And inside you have one proton, just one quantum proton, which initiates, for example, the catalytic process. So if I would like to simulate such a system, I'm thinking of dynamics, quantum dynamics, classical dynamics, and a coupling. Then I would have problems, for example, to determine what are the lambda and gamma parameters. I mean, this kind of heuristic parameters. I mean, so the first question is, could you, based on microscopic interactions and definition of the model, could you determine values of these parameters? That's the first question.
Right, so the lambda and gamma parameters, they're important for feedback. They're not important for the EMME, you don't need them. For the quantum Fokker-Planck master equation, they are heuristic parameters that we put there that describe our detector, because we don't have a microscopic model of the detector. In certain cases, I'm sure you can derive them from a microscopic models, but probably not in all cases. But for the EMME that works for finite size environments, you don't need them. You don't have any parameters that you put by hand.
I mean, if you think of the dynamics,
Yes.
the most important problem is how the quantum domain influences the dynamics of the classical domain. That's the most important problem.
Right.
But if the structure is flexible, right?
It might be that then what you're describing, it might be that the EMME doesn't apply, right? Because in the EMME, we think of a quantum system, so like in the sketch here, that system can be fully quantum and have quantum coherence. The environment needs to obey certain assumptions that effectively make it classical. Still dynamic, but classical. If there are quantum effects in the environment that are relevant for the system, our approach would break down. One of the assumptions would break down.
Okay, so another question is the following. Did you check what are the energy conservations for the quantum domain and classical domain? If question is, if in your model you don't observe, for example, a systematic drift of the energy between the classical and quantum domain.
Yeah, that's
something which we observed in supercomputing simulations.
okay.
It was a headache for us.
Yeah, that's a very interesting question. So this is actually being addressed by Philipp Strassberg and co-workers in this PRX Quantum or in a PRE. They published two papers kind of back to back. I'm not quite sure which one. But here they showed that this equation essentially, that this conserves energy. That the average energy in the quantum system plus the stochastic energy of the environment is always conserved.
Right.
But in your case, isn't it a problem that you have more parameters than just energy to describe this classical system? This would be the issue, no?
In principle, you can, I mean, we do it for the magnetization, which in our case kind of reduces to the energy. In principle, you're not forced to do it with the energy. If you do it with the energy, you do have this energy conservation. I'm quite sure if you would do it with something else, energy conservation would take on a quite different form. And as is also the case actually in Lindblad master equations, where if you're not careful, you will get stuff that violates the laws of thermodynamics. And that's because we make approximations, and these approximations, they don't necessarily respect things like energy conservation or increase of the second law of thermodynamics. So as soon as these violations are then kind of big, probably one of the approximations somewhere broke down. But you're not guaranteed that these laws hold, because you do make approximations here. Usually there's ways to fix it, but they can be quite subtle and non-trivial.
Maybe I intervene. We're happy to have more discussions, but I think we need to close for the students to go, so that let us thank Patrick, and surely you can talk more, no?
See you next semester.